Today, let's talk about orbits. One of the main things about orbits is the altitude that the satellite or the spacecraft is at. So there are three main areas where we put satellites. The first is low Earth orbit, which is technically below about 2,000 kilometers altitude. Most satellites are actually closer to 700 kilometers altitude, but the technical definition is below 2,000 kilometers altitude. These are primarily weather satellites, communication satellites, imagery satellites, and military satellites. Now, this next thing above 2,000 kilometers is medium Earth orbit. This is where mostly our GPS satellites are at, and they're around 20,000 kilometers altitude, and they have orbital periods that are about 12 hours, which is half a day. And so they basically have this ability to come back over the same longitude every day, which is an important and interesting feature of the orbits. Then the next one, you go out even further and you're at geosynchronous orbits. And geosynchronous orbits are around 35,000 kilometers altitude. They're mostly used for communication satellites and weather satellites. One of the primary important things about an orbit is the inclination of the orbit. The inclination of the orbit is the angle between the satellite's orbit as it goes through the equator. So as it's going from south to north, it makes an angle with respect to the equator, and that angle is the orbit's inclination. Interestingly, the inclination, that angle, if it's below 90 degrees, also marks the highest latitude it reaches and the lowest latitude. So here are three examples. The first one on the left is an equatorial orbit. So the satellite is basically staying in the equatorial plane of the Earth. And so it has a 0-degree inclination. The one on the right is a polar orbit satellite. So it is going over the poles. And so it has a 90-degree inclination. And the one in the middle is an inclined orbit. And so it actually has like about a 45-degree or so inclination. Polar orbits have basically the characteristic that they go over the entire Earth. If they pass over the poles, that means they're going from pole to pole and they're covering the entire globe. And so if you want to see the entire globe, then you want a really high inclination orbit. And most weather satellites want to see the entire globe, and so they usually have really high inclination orbits. Then there's this special orbit called a sun-synchronous orbit, which we basically put at a very precise altitude and inclination that stays in a fixed local time. When we talk about the definitions of some of these things, we have what's called the ascending node, which is as the satellite is going from the south to the north, and then when the orbit is going from north to south, it is the descending node. So in every orbit, you basically go around the Earth in a complete circle, and you go through two phases. The first is that you go through the ascending node, and then as you're going down, you go through the descending node. Ascending node, descending node. Let's talk about what's called a sun-fixed coordinate system. So when we talk about orbits, we basically have the orbit going around the Earth, and underneath that orbit, the Earth is rotating. And the satellite orbit plane is actually in sort of a local time of ascending node plane. And let's go through what that really means. So in order to understand that, let's talk about local times. When we look at the Earth with respect to the sun, we have towards the sun, which we define as noon. If we go away from the sun, we have midnight. And then we have dawn and we have dusk. We think of it as the sun is coming up and the sun is going down. But really, the Earth is rotating through this coordinate system, this sun-fixed coordinate system. And it basically stays like this with the Earth rotating underneath it. The local time stays fixed. Satellites orbit in this local time. The orbit stays fixed while the Earth underneath rotates. So this example is showing what's called a 3 a.m. local time of ascending node. As the satellite is coming up from south to north and it's crossing the equator, what is the local time? We can see in this that it's between midnight and dawn, and it's roughly 3 a.m. All right, so that is a 3 a.m. local time of ascending node. Now, if the orbit plane is oriented like this, then it is coming up from south to north between dusk and midnight, which is roughly 9 p.m. or 21 out of 24. So it is called a 21 local time of ascending node. And we can move this orbit plane all over the place. So this is a 3 p.m. or a 15 local time of ascending node because it's between noon and dusk. And here we're showing a dawn to dusk orbit. So it has a 6 a.m. local time of ascending node. Now, we like to show ground tracks of the satellites so we can see like where the satellites are with respect to the globe. And so this is showing a ground track. The way that you derive a ground track is you go from the center of the Earth out to the satellite, and where it goes through the surface of the Earth, you draw a point. Now, interestingly, like right here, you can see that those satellite tracks where the satellite is and one orbit later don't match up. And the reason that they don't match up is because the Earth is actually rotating underneath this. Remember that the satellite orbits in this local time plane, but the Earth is rotating. You are not at the same place. You don't come back to the same place because the Earth is rotated. Let's move outwards a little bit and let's talk about geosynchronous orbits. Geosynchronous orbits are very interesting because the satellite is pretty far away from the Earth, so the orbital period actually is quite long. Instead of at low Earth orbit, these orbital periods are only like 90 minutes. At geosynchronous orbits, the orbital period is almost exactly 1 day. It is 23 hours and 56 minutes. And so it actually stays roughly over the same point on Earth all of the time. That distance from the center of the Earth to the satellite is about 6.6 Earth radii, which is 42,000 kilometers. Now, these satellites are very useful because they're pretty far away from the Earth, and you can put a camera in there that can see a large swath of the Earth, a big chunk of the Earth. And so we put these weather satellites at geosynchronous orbit, and they take pictures of the Earth. And they take pictures in different wavelengths, which tell you different things about the weather. And you could see this hurricane that actually has hit Florida here and is moving up in the Gulf of Mexico. There are also a lot of communication satellites in geosynchronous orbit because they basically stay over a fixed position, and so you can communicate to a place on the Earth all of the time. We talked about weather satellites being in geosynchronous orbit and weather satellites being in low Earth orbit. And why would you mix these two things up? So this is showing a hurricane hitting Florida here, and then it's going to zoom in, and you can see the track of a low Earth orbiting satellite taking the same type of data. And then embedded in this, you see this really fine scale resolution. And that fine scale resolution is from the low Earth orbiting satellite. And that coarse large scale resolution is from the geosynchronous satellite. So you can combine these two satellite systems to get both really fine scale detail and large scale detail. Now, why don't we just use like a ton of low Earth orbiting satellites? Well, because these low Earth orbiting satellites orbit around and then the Earth rotates underneath them, by the time the satellite comes around again, Florida is now gone, and it's going to go over Alabama instead. And so if you want to monitor what's happening in Florida all the time, you would need a huge number of satellites going around, basically in different local times of ascending nodes, so you could measure it over and over and over again. And it's not necessarily worthwhile to put that many weather satellites in orbit. More details about geosynchronous orbits. If it is sitting in the equatorial plane, basically with a 0-degree inclination, it stays over a fixed spot. But that fixed spot is actually on the equator, and it doesn't really move much with respect to the Earth. But you can play with the orbits and have them do interesting things. You could make this orbit so it's tilted, so it actually has an inclination, and you can see that we've inclined that orbit around 40 degrees or so, and so it actually tilts up. Why would you want to do that? Well, if you want to go off the equator, let's say that you actually want to see like the northern parts of the United States or Canada or Russia or Greenland, for example, then you need to go to higher latitudes. Because if you're at the equator, you can't necessarily see those locations. But if you incline yourself a bit, incline the orbit, you can actually see to those high latitudes. The next thing that you can do is you can make it so the orbit is eccentric. So it basically is longer on one side and shorter on the other. What does that do? Well, so it makes it so you go really fast when you go close to the Earth and really slow when you go far away from the Earth. Satellites sometimes combine this inclination, tilting of the orbit, and this eccentric orbit to do interesting things. Sirius XM radio is satellite radio. And what the Sirius XM radio satellites do is that there are 3 of them, and they are in geosynchronous orbits, but they are highly elliptical orbits, and they are inclined. So they go up to Canada, and then they go down to, South America, south of South America, actually. And what happens is that they zip around South America very quickly, and then they come up over the United States, and they hang above the United States for long periods of time, and then come back and zip around South America again, and then hang above the United States. And so you can get really good coverage with 2 satellites. They have 3, one is a spare. If it was at the equatorial plane, it would have further to travel to get to us, and so it wouldn't hang there as well. The signals would not be as good. With the elliptical orbit like this, you can have an antenna that's pointed upwards, and so it's a better setup for a car. So in summary, there are a lot of different types of orbits. Low Earth orbit is below about 2,000 kilometers altitude, and most satellites are sitting there. The inclination of the orbit tells you the maximum north and the minimum south latitude that you go to. Polar orbits are 90-degree inclination, and they pass over the poles, and they're useful because they give you coverage of the entire globe. Satellites orbit in local time, with the Earth rotating underneath them. Geosynchronous satellites have an orbital period that is exactly equal to the rotational period of the Earth, and that allows them to stay over a fixed location, roughly a fixed location on the Earth constantly. And then you can incline those geosynchronous orbits, and you can make them elliptical, and that allows you to sort of hover over a spot that's not at the equator, so you can get good coverage at that location.